As a reminder of where we are in fact around at this portion, okay, but in fact we will still talk about something about this, alright, and it's regarding a more in-depth thing with relevance to, where's my pen, with relevance to superelastic and shape memory. So these are the two things that will be discussed uh, in this video, and in a very rigorous way, alright. And we previously somewhat stopped here, alright, is that the shape memory alloy deforms plastically under a stress, but return is blah 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 when it heated. So we said that the ordinary metal material is like that, alright, but except compared to shape memory, alright, when you heat, alright, you can actually go back to the original one. For over here, the normal metal, when you load it and unload it, alright, you will not go back to here. You will not go back. For shape memory, can. Okay. As such, this is one thing regarding of this type of shape memory alloy. They call it a nickel titanium shape memory alloy. Okay. And this thing is a deflection, and this is a temperature. So how do they, check it out? How are they different? Our belief is that during, when you heat it up, your this is a spring, I think. All right. So you heat it up over in this region, okay? Heating, and you heat. And once you heat to 120, alright, it's always the same. Okay. This is the line that is the greatest deflection due to temperature. Alright, the cooling and the heating. So over here, this is the highest, right? Up to here at this particular point, which is about maybe, this is what, in between 40 to 60, I think most probably is 50 degrees. So about 50 degrees Celsius, it can start to actually deflect, you see. So there's a point where heating up, you require about 60 degrees, or this point is about 60 degrees Celsius in order to so-called sustain its or 60 degrees Celsius, it will reach its maximum deflection. Alright, meaning it will stand up like that. Okay, at 50 degrees Celsius, alright, 50 degrees Celsius, it will start to actually go back to shrink back to this thing, to this size. Alright, so in between this whole shrinkage, alright, is the whole total deflection over here. Okay, so hopefully you kind of know what I'm talking. And this is in terms of millimeter. So approximately this is about I guess 60, not 60, but rather 50, 57. Alright, and over here this is most probably maybe 10, I don't know. So in between them they have the total deflection to the maximum deflection is 47 mm. Alright, and yeah, so this is somewhat the graph of it, just to show you the deflection of the nickel titanium. And the key thing just to take note is the heating and the cooling. Alright, this is not discussed in the lesson, but I think I'll just briefly explain, and then explanation may be a bit wrong, but nice thing is that when during heating, right, it takes 60 degrees Celsius to reach this thing, but you have a 10 degrees Celsius difference in order for the deflection or the thing to shrink. So there's a 10 degrees Celsius difference before the spring itself starts to shrink back into its original shape. So this is a form of a so-called shape memory alloy, and nickel titanium is actually one of it. Alright, so it can be used as a thermal sensor and actuator. Alright, not just withstanding to super elastic alloy. Alright, shape memory alloy can also be so-called activated as a thermal sensor actuator thing. Okay, and then shape memory are also used in lower application. So what is a lower? In order to illustrate the lower's meaning, alright, let's take a look on this thing. Alright, how the lower is being made. Okay, so if you were to look closely, right, you see this is actually a lower. Alright, so if I were to draw it out, I have this kind of like, I don't know I don't know whether you can understand what I'm drawing. Alright. So for example, if I have a wind, maybe blue color wind, alright, it blows in. Alright, it blows and then it follows this curvature and then goes in like that. And woo, go in through like that. So it allows the airflow to goes in this direction. So that somebody, maybe if you're sitting here, you can feel the air, you feel very happy, type of thing. So therefore this thing over here, this method of lower, alright, lower, is being used in automotive or aircon. Okay, so aircon is, so when you have a so-called low temperature air conditioning that is happening, if you were to, you feel very hot, so you on your stuff, okay, you on the aircon to the max, alright, due to the deflection, if you remember just now, the cooling thing, or the cooling, when you cool the so-called the metal, alright, or the nickel titanium alloy, you will actually have lesser deflection, or you will have a lesser deflection. So when you have a lesser deflection, I don't know which side you'll turn. Maybe you can go up over here, or maybe you can shrink back over here. So you actually alter the level of the wind, alright, or the how the wind blows. So for example, if it's angled, so because of the deflection over here, this piece, right? Maybe I should draw. Never mind. This piece over here may actually rise a bit if it's hotter, or if it's colder, then maybe you'll kind of like go smaller, and like, if I were to go into side view lah, okay, this is the side view and this is the lower. Alright, so the wind will actually go in and you like woo, right? But however, if the air is actually colder or hotter, I don't know, it may actually rise a little bit. Alright, so all of them may rise a little bit. Then you allow more air to go in, right? You allow more air to go in. So because of this curvature over here, so you no need to use your hand to actually adjust the air conditioning and things like that. Okay, so this is a way to illustrate on the louvers application, and at least you get to understand. So I'll just highly suggest that you could also where do I go? So if you were to go to shape memory, you give me a while, lower shape memory, okay, the first thing you'll find is development of automotive this thing. Okay, then you go and press it, right? You enter somewhere over here. Alright, some schools from Malaysia. Okay, yeah. So if you were to go in furthermore, or you should come kind of like get here already. And is that they also will talk about the things of austenite and martensite structure. Okay, showing the different things. It says that the martensite will transform into austenite, alright, by increasing the temperature or removing the applied stress. And it gave us a very good table of the austenite thing. So for the austenite, the Young modulus is this thing, you see, 30 to 83. Martensite lower. Okay, ultimate tensile strength the same. Alright, elongation same. Alright, Poisson ratio, everything same. Just the Young's modulus is different. Austenite is more so-called, the higher the Young modulus, the stiffer it is. So austenite itself is more stiff than martensite. So the austenite is something that is during high temperature, then it will exist. Alright. So for example, when austenite is cool very suddenly, alright, austenite is always in the highest temperature, alright, and this is why it explains it has a very high stiffness, alright, 30 to 83 GPa. Okay, so austenite itself, if you still remember, I keep showing you the certain graph you give me. Okay, so during your austenite region, alright, it's in this region. If you think about it, this is in the temperature. Alright, so austenite only exists during a certain temperature only. This is the highest temperature. So it has a very high stiffness as being shown on this slide. Okay, however, this is only in its highest temperature stage, alright, which is above 1000, so it's something unrealistic if you were to use it for normal application. Okay, So over here, right, you will either quench it very fast or cool it very fast. Alright, within seconds, it becomes cementite, which this is called martensite. Okay, which is martensite is the most hardest form of things. Okay, if you cool slowly, you become pearlite. Alright, or ferrous metal. So we are going in this region, which the the strength is softer than cementite. Okay, hopefully this kind of remind you in the past of whatever thing that I'm talking. Okay, at least you get a feel of things that I'm trying to explain. Alright, so therefore martensite is the hardest form of each already. Okay, it's the most stiffest. Okay, but please take note that martensite, alright, although it is high Young modulus, which is stiffer, alright, the yield strength is not determined by martensite or ferrite or whatever. It is determined by the finer the gabites and the grain size. Grain size, and most people you know, alright. So the higher the more fine the grain size, the higher the yield strength. Okay, and carbide. Alright, carbide, let's take a look what is carbide. So carbide is a binary compound of carbon with an element of blah 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 blah. So it's, in other words, a carbon so carbide itself is a carbon compounded with a non-metal. Alright, so I think it's mixing with other stuff like boron, calcium, silicon, etc. So it's just a form of things that this mixture, because normally you want to create an alloy, you need to mix with other like calcium, chromium, whatever. So when you mix it, different type, like for example chromium carbide, the green structure will be different. If it's calcium carbide, then the green structure also will be different. So it depends on the green structures of your mixture and your etc. overall thing. So this therefore will affect your yield strength. So this is a very so-called good finding. At least we know how yield strength is being affected. Okay. So the tempering determines the size of the carbide particle. Increasing the tempering temperature for a given time will accelerate diffusion, but lead to the carbide and grain coarser and the material is slightly softer. In this case, the yield strength will reduce more than hardness. Okay. So because tempering itself, if you remember, I think tempering for what? The purpose of tempering chocolate is chocolate. Oh, tempering itself is already reducing the hardness of the material, or making it ductile, or creating it to be tough. So normally you would want to temper before you harden. Why? Okay. So I would believe, right, if you temper your material, for example, this is, give me a while. So imagine you have this material. Okay. So or maybe most probably I should use a katana explanation, you know, those Japanese type of thing. So if you were to, this is a cool samurai sword, you know, wow. Okay, this explanation may be a bit sucks, but anyway. So you just if you were to just created this so-called katana, you'll temper it first so that every here and then will be soft, ductile. Alright, and over at this edge, alright, at the edge where you want to cut people, right, you want to be hard. So therefore over here at this edge, you will have to change it to austenite first. So before changing austenite, you make the whole material to be tempered. So in other words, all this region over here in blue, alright, they are all very ductile. Alright, while over here in this side is austenite, where it is kind of very hard. And when you quench it or you cool it very fast, quench it, you'll become martensite, which is super ultra hard. So if you think about it, you split your katana into a very hard, so-called the cutting edge, you put it as very hard, while the back edge you put it as a ductile. So when you hit, when you somewhat kind of hit with some other hard material, alright, this part over here may be hard and hard will actually create an impact. So the impact is being brought over to this ductile side, for example. So the ductility over here will actually prevent, because when you have two sword fighting, alright, over here the hard one over here will hit with the other sword. So if this part over here is weak, it's kind of like very hard, it taking the impact, but because it's very brittle, alright, it may actually break, and then your katana will break. So therefore over here, when it reaches over here, there's an impact. This impact will brought over to the ductile side at the back. So the ductile side over here will take in the impact and actually releases it. so therefore it will not break your katana, and therefore it's a mixture of ductile and hardness all together as a katana, and therefore it helps you in having or helps you to achieve a certain good material that is able to be hard while also not break to a certain extent. Okay, so hopefully this clear a lot of stuff that is going on. And the super elastic alloys, super is super now, not shape memory already, is also used for orthodontic teeth, which we have said in all along. Alright, and the main feature of this type of shape memory or super elastic alloy are all this high recovery force, etc. I don't think I need to explain much. I think the high recovery force is talking about recovering back to its original state. Alright, because maybe sometimes if you were to load it or unload it, you may change the overall strength of the material. So when you heat it up for your shape memory, you can actually return it back to its original strength. So this is what it's trying to say, I believe. Okay, and total silent in operation, I think you know. Alright, large recoverable deformation strain up to 6% for a few cycles. So for example, large deformation strain is, let's say you have this material, alright, and if you were to strain it for 6%, alright, so it has a very so if you were to strain it at 6%, you can actually, when you release or unload your stress, it can actually go back to its original shape. So it can be able to take in 6% of strain before it for a few cycles, alright, before it starts to yield permanently, but not permanently, rather than yield at this point. Alright, maybe, yeah, before it starts to yield at this point and then you reach here. So in order to return back to your original thing, then you have to reheat back, but it is able to take in about 6%, alright, elastic region, okay, before it kind of fails. Hopefully this clear things up a little bit. So it is good, has a good resistance to fatigue, alright, by controlling the strain. Because of the 6% thing over here, you can control the strain quite relatively well. Alright, so you can restrict the fatigue, because if you have a very big strain allowance, because your fatigue normally is a cycle, alright, so if your cycle is within the 6%, alright, or maybe I should say maybe 4% for example, which is also within 6%, or 3% or whatever, as long as it's within 6%, you will not have any fatigue at all, alright, because it is within, it has a good resistance to fatigue because it can take in a lot of cycles, and because of the strain itself is 6%. If you were to exceed 6%, then you yield, but if you were to within that, actually is very safe. So this material is good for fatigue application, alright, to restrain any or to resist any fatigue at all. So it can be used for long life applications, as it says. And corrosion resistance, I know you say biocompatibility for medical applications comparable to series 300. So biocompatible, let's talk about what is it. The meaning is a material that is used for surgical implants, not harmful for toxic to living tissue. So it's just a material that is compatible to biology. That's just the meaning of that. It's compatible to biological aspects. So it's compatible to living tissues. Yeah, whatever lah. So therefore it's good for medical applications compared to 300 stainless steel, which is expensive, I think, and I don't know what the hell, but yeah. So entering into the last part, but we will take a little time more. Alright, so let's continue. The most common configuration for a shape memory actuator is wire wound into a tension or compression during shape, giving large stroke. So it's often going as a spring, which is what we have shown you earlier in this spring thing also. So for a shape memory alloy, it is always good to apply as using a shape memory alloy for a wire. Alright, so the making of a spring involves hard drawn whatever, in this is the so-called manufacturing process. Okay, so think about it, is giving large stroke. Alright, so this type of stroke, it means that you actually create maybe I should show you picture. You can actually go to large stroke spring. You should be able to get to here somewhat over here. Can feel get a like sharp stroke front damper. So if you think about it, it's more on the damper side. So I think it's able to resist so-called any stresses due to any forces. It can damp out anything. So I don't know how it's exactly being applicable in all this scenario. Alright, these are all the things that you may have been familiar with. Alright, the damper and the spring. But to be a more exact thing, I think it is used for damper application, I guess. Alright. If you're free, you can go and read it up yourself. I kind of lazy already. So you just need to know that it's making for anyway. So our concept of differential actuators. So you can use your shape memory as a actuator. It's still a spring. It's not a damper at all yet. Alright, by the logo over here is a spring. So upon heating or cooling, it may move in different thing. So you may heat up this thing and then you cool it this thing, so the mass will actually move over here. If you want to cool and heat up, vice versa, it will move over here. So it's a form of actually moving your mass, or it's using heat. So the actuator over here is to use the heat to actuate the spring or this type of shape memory alloy, so that they will deflect and move the position of the mass from one place to another place. I think this is the application by Hiroyoshi Funakubo. I don't know what I'm talking, but anyway. And this is the equation that is being used for the spring, and yeah, what the hell. So the G is your modulus of rigidity. Alright, it's also over here. This is your Young modulus. If it's an isotropic material, your Young modulus is just the Young modulus E. The Poisson ratio is just a Poisson ratio. If it's something like E1, one direction or two direction, is a one direction, two direction. If they are anisotropic, then you're gonna talk about different stuff like E1, and then this is V21 or V12. I forgot. Maybe I should go and find it out. Never mind, you should go and find it out. I lazy to find, but I think most probably is V21 or Poisson ratio 21. It's in the composite size. Alright, never mind. I go and find. Being for a long time, E2 and V12. Alright, as you can see. Alright, so in our case, it's actually, for example, if it's E1, then I would say that it's Poisson ratio 1 2. 2 1, sorry. So it should be E21 as correspond to this. If it's E2, then you use V12. If it's E1, then you use V21. Yeah. If it's E3, then I think you can use some other things. I think it's V31. Yeah. Anyway, so this is the shear modulus. This is the number of let me think. After verifying with this website, alright, if you think about it, it's the wire diameter. Alright, if I were to just show you, this D, small d, is the wire diameter. Alright, the capital D is the mean diameter, which is the total coil diameter. Alright, so if I were to head back to here, then this is actually the so-called the diameter of that particular thing. This diameter. Or this big one is the so-called coil diameter. And what is delta? Spring deflection. Alright, this thing is spring deflection. How much is being deflected, I guess. Amount of deflection that occurs. Pi 3/14, and number of turns, 1. Over here there is 1, 2, 3, 4, 5. So there's 5 turns, so number of turns 5. Then K is the constant of the spring, while what is P? Good question. P is the pitch diameter. Alright. Not pitch diameter, not gear. This is the pitch. Alright. So it's from the mid of the mid of this circle to another mid of the circle. Alright, because these are all made of a circle chord. I mean, this type of thing, so they are rounded. Alright, all along and along like this. My drawing sucks, but anyway, so this is the distance, the pitch, P. Alright, and where are we? Alright, so I think the rest is, I think you know already. So the K you need to know, and normally I think you'll be asked to find the constant. So in order to find this constant, you need to know the deflection, the here and there, the this is the diameter of the spring, I mean the materials lah. This is the total diameter of the coil and things like that. I think it's somewhat there already. In fact, this is a very in-depth approach to what I've said, and also to show you this or to explain deeply into all this stuff. Okay, but I also want to tell you that the K constant, alright, can be found by this thing. Alright, so I think you need to know how to find also. Alright, you take the coil diameter divided by this diameter. This is D, this is the D. So I think you know what to find already. So I think this is it of explaining everything about simultaneous equation. Shape memory alloy. Alright, I don't know what I'm talking, but anyway, yeah. So next video I'll talk on into the little sidetrack. Alright, talking about prediction of buckling at maximum load in a steel column by buckling stress and critical stress, which is this thing. I don't know what the hell is shiggly, but I shall see you in the next video. Goodbye.